It's working? Yeah. So good morning, everyone. Welcome to the second week of this conference. So today we're going to start this morning with the first of four lecture series by Subhroshekhar Ghosh from the National University of Singapore, who's going to talk about complex stochastic models and applications. Please, sure.
Okay. Thank you, Pierre, for the introduction. And thanks a lot to the organizers for organizing this great program and having me here for the series of talks. So I'm going to talk about complex stochastic models and their applications. And basically the plan of the talks is as follows. So in the first three talks, I will cover three disparate topics. So today it's going to be on spin systems and quantitative Marcinkiewicz theory. And the next, tomorrow it will be about the problem of learning under group invariances. And the day after it will be about determinantal processes. And on the last day, we will come back to the problem of learning under group actions once again and explore some more nuanced structural properties. So today we are going to focus on, the idea is that the first three lectures are going to be standalone. So you could, just listen to them as individual lectures. So today we are going to talk about spin systems and quantitative Marcinkiewicz theory. And we are going to start from the second part, which is the Marcinkiewicz theorem and its extensions. Okay, so Marcinkiewicz theorem is the theorem about Gaussian random variables, and so this brings us to to the starting point of the theory of Gaussian fluctuations, which, as we all know, has a long and illustrious history, and most approaches to Gaussian fluctuations involve approximating your objective for which you want to prove Gaussian fluctuations by an appropriate low complexity function. And this low complexity function should be a function of roughly independent or weakly dependent random variables. And these random components should individually have small influence. So none of them should be much bigger compared to the others. So if you are able to express your objective function by a relatively simple function of weakly dependent random variables, each of which is individually small, then I think there is some kind of sort of a moral or heuristic understanding that such a situation should lead to a Gaussian central limit theorem. So for example, this includes, within the ambit of this discussion is included the classical central limit theorem for sums of weakly dependent random variables, or independent random variables, if you look at the De Moivre-Laplace version, to so-called invariance principles, which have become popular in recent times due to their applications in computer science and elsewhere. So, for example, we can consider this reminds us about the invariance principle and the Gaussian fluctuation theory for low-degree polynomials for independent random bits. And one of the important works in this direction is due to Mosel, Oleszkiewicz, and their co-authors. And in between this spans a lot of other possibilities. But this is just to sort of set the stage and the historical background. And I am skipping a lot of important works here. So my apologies in advance for that. But this is really the background. And we are the whole point, which we are going to see in the next slide, is that we are going to sort of take a different point of view in this talk and try to see what we can get. So this brings us to Marcinkiewicz theorem. So Marcinkiewicz theorem is a classical theorem in probability/complex analysis. So suppose you have a random variable x, and suppose you consider the characteristic function of the random variable, And suppose this random variable X has, its tails decay fast enough so that this is a this is an entire function in the variable u. Okay, so psi x is an entire characteristic function. So already it is addressing a somewhat limited class of random variables, but but still it covers a lot of important examples. So if psi x is an entire characteristic function, and suppose this entire characteristic function is of the form e to the power of some polynomial p. Okay. So then, if you leave out degenerate cases, so if for example, if the random variable is constant, then you can see that the characteristic function psi x is an entire function, and it will be e to the power of some linear function. But that is the degenerate case, and if you leave out the degenerate case, then if the characteristic function is an entire function as a complex function and is of the form e to the power of some polynomial, then this polynomial has to be a quadratic, and this random variable x has to be a Gaussian. So this is just a refresher on the classical Marcinkiewicz theorem. It is somewhat remarkable theorem, and the key point is that it is deeply complex analytic in flavor. In some sense, this reflects on some kind of rigidity properties of the class of entire characteristic functions. And at this point, I would like to mention that entire characteristic functions, it has been a topic of its own interest for a long time, particularly in the middle of the past century. And we will see some of the names of the key researchers in this area in the next few slides. So this was Marcinkiewicz, and he came up with this theorem in 1939. And before discussing the consequences and the follow-up works on this theory, let me sort of make some observations regarding the conditions under which Marcinkiewicz theorem holds, and this will already sort of give us some indications or clues as to how we can hope for a more robust and more extensive theory. So observe that if your characteristic function, we will always assume that it's an entire function. But even so, if your characteristic function is of the form e to the power of some e to the power of f for some entire function f, so then this is equivalent to saying that your characteristic function doesn't have any zeros on the whole of the complex plane. And this function, this e to the f, this function is a polynomial. Roughly, you can think of saying that. Roughly, you can think of it like this: that if your function psi is of the form e to the f, then f is essentially log psi, and log psi is of polynomial growth. And basically, if for entire functions, there are severe limitations on how a function can grow versus what its structure can be. So roughly speaking, we can summarize or we can extract the criteria of the Marcinkiewicz's theorem as follows: that the fact that the entire characteristic function is of the form e to the power something, this can be abstracted by saying that the entire function, the characteristic function, doesn't have any zeros, and that the fact that this e to the f, this f is polynomial, we can sort of encapsulate it by declaring that this log of the characteristic function is of polynomial growth. And the very fact that the log can be taken as an analytic function is a consequence of the fact that psi has no zeros on the complex plane. Okay. So, by the way, so if there are any questions, please feel free to stop me at any point. And so before moving into the quantitative Marcinkiewicz theory, which is one of the main topics of this talk, we will discuss the follow-up research which has been spawned by Marcinkiewicz's classical theorem. And really, and one important question which was raised in the middle of the past century was, what are the optimal conditions under which Marcinkiewicz type theorem holds? So to this end, we will have use for this function MF. This is a useful tool in this topic. So let's define it. So MF is basically the maximum. It's a function of positive reals, and it's a maximum of the absolute value of the log characteristic function on the disk of radius r. Okay, where r is the argument. So MF of R is the maximum of, essentially this MF of R is introduced to deal with the maximum of the log characteristic function. And basically the way this is going to enter the picture is that we are going to discuss the growth of MF, which, in the context of the condition that log psi should be a polynomial growth in Marcinkiewicz's theorem. So it is an immediate observation that if MF of R is the sort of the size of the log characteristic function on the disk of radius R, then if log MF over R is positive, then this does not fall within the ambit of Marcinkiewicz's theorem. So for example, just to sort of remind ourselves, if X is a Poisson random variable, then roughly speaking, it's at least in the sense of up to smaller order terms, its characteristic function would be of the form e to the constant times z. So this log plus of MF is essentially log of the characteristic function. So if log of the characteristic function divided by R doesn't, it is positive, then this contains the Poissonian example as a particular case, and therefore we cannot hope for a Marcinkiewicz type Gaussian identification theorem in case if this event happens. Okay, if this condition holds. So basically, if you think of the growth of the log characteristic function, then essentially in the asymptotics of this quantity log MF over R cannot be positive, and therefore the natural thing to consider is the situation where the log characteristic the log characteristic function, which is log MF, divided by R, it goes to 0 as R goes to infinity. And in 1960, Linick, pursuant to the work of Ostrowski before the Second World War, Linick conjectured in 1960 that Marcinkiewicz type theorem should hold if as soon as this Poissonian example is ruled out, basically. And so this was Linick's conjecture. So as soon as the log characteristic function sort of grows only sublinearly, we should get a Gaussian identification theorem on the lines of Marcinkiewicz. And Ostrowski, a few years later, confirmed that Linick's conjecture is true, and in fact he provided a better condition that he proved in another condition that lim sup is 0, and using ideas from Wim and Varillant theory. But this is like the historical follow-up on Marcinkiewicz's theorem. So all of these theorems, Ostrowski's theorem, for example, assumed that the characteristic function of the random variable is still entire, and in return it gives you an exact Gaussian distribution, an exact identification with a Gaussian random variable. So here we are interested in quantitative Marcinkiewicz theorem. So quantitative or stable versions of classical qualitative theorems have gained importance in recent years. And in a similar vein, we ask the question as to whether we can hope for a quantitative Marcinkiewicz theorem. So we want a quantitative or a stable version of the Marcinkiewicz theorem, and as we shall see, this will provide us a route to obtaining central limit theorems in situations where the existing theory does not seem to be applicable. So if you want a quantitative, so what are quantitative or stable versions? So basically, we assume that the conditions of the exact classical or qualitative theorems. They do not hold. They do not hold in totality. Instead, we will assume that they hold only approximately, and in return, we will get not an exact Gaussian identification theorem, but instead we will get a Gaussian approximation theorem. So in summary, we will try to say that our random variable satisfies some conditions which are sort of approximate versions, quantitative versions of the conditions of the Marcinkiewicz theorem. And in return, we would expect a statement which is quantifying how close our random variable is to the Gaussian distribution. Okay, so that's what we are shooting for. So the natural hypothesis, so psi x is of the form e to the f for some entire function f. So this was the hypothesis in the basic hypothesis in the Marcinkiewicz theorem. And as we already saw in a few slides ago, this is equivalent to saying that psi has no zeros on the whole of the complex plane. And in the quantitative version, it is natural to replace the condition that psi has no zeros on the entirety of the complex plane by the condition that psi has no zeros on a disk of radius r. And you could imagine that it's natural to imagine that we are thinking of a situation where r is large, but as we shall see in certain applications, it is important to take r small. And the natural conclusion, so this is the natural hypothesis, and then there will be some growth, there will be the growth of the characteristic function on this disk of radius r would come into the play. But the natural conclusion that we are expecting is that exact Gaussianity, as in the classical Marcinkiewicz theorem, will be replaced by the distance of your random variable from a Gaussian, some bound on the distance of your Gaussian random variable from Gaussian, and this bound, this degree, the quality of the approximation should depend on how big your disk is, and the growth rate of your log characteristic function on this disk on which it has no zeros. So remember that as soon as your characteristic function has no zeros on this disk of radius r, then on this disk we are allowed to play the same game. We are allowed to consider the log characteristic function, and we will the growth rate of the log characteristic function on this disk will be a key determinant in the quality of your approximation of x by a Gaussian. So this is what we are aiming for. So let me state the quantitative Marcinkiewicz theorem without further ado. And this is a joint work with my colleague T.C. Din and my students H.S. Tran and M.H. Tran, and one of them is with us in the audience. So feel free to ask him questions. So the assumptions are as follows, as we discussed. So we assume that the hypothesis entails that the characteristic function doesn't vanish on a closed disk of a certain radius r, and then we have an approximation of. So this is the centered version of the x bar is a centered version of your random variable x. And small phi is the characteristic function of the Gaussian. And this is supremum of over x in R. So this is basically the Kolmogorov-Smirnov distance between. On the left-hand side, what you are seeing is the Kolmogorov-Smirnov distance between the centered version of your random variable and the standard Gaussian. And this is less than equal to, so there are two terms. The first term is a triviality. So for example, this is sigma is the variance of your random variable x. So, if the variance is not 1, then of course you cannot expect a good approximation by a Gaussian. So in general, it would be natural to sort of, normalize, center and scale your random variable so that this sigma is 1. So the first term is kind of, it's a sort of a minor term, a less important term. The more important term is the second one, which is constant times the size of the log characteristic function on your disk divided by r. And this should exactly remind you of the content of Linux conjecture, and which was later made into a theorem by Ostrovsky. So exactly we get this kind of Ostrovsky bound by on the distance, on the Kolmogorov spin of distance between your random variable and a standard Gaussian by quantities which are reminiscent of the criteria of Linux conjecture and Ostrovsky's theorem, which are follow-ups of Marcinkiewicz's classical result. Okay. So this is the quantitative version of the Marcinkiewicz's theorem. So let me now okay. So one of the things which I mentioned is that quantitative versions of classical theorems are of interest in themselves. But one way we would like to use them is that we would like to use them to prove central limit theorems, and one can kind of see how it's going to work, because if you have a random variable of interest, a sequence of random variables of interest, and you want to show a Gaussian central limit theorem, then you would want to sort of apply this quantitative version to, you would want to find a disk of radius Rn, which depends on the index n, on which, and show that your characteristic function of xn doesn't vanish on that disk, and then apply this theorem to show that this right-hand side goes to 0 as n goes to infinity. But in order to, so you can see that this should naturally lead to a method for obtaining CLTs. But in order to make it, use this result as an off-the-shelf result for as a CLT proving technique, we have a version which basically does exactly that, lays out the details for you. So you, for every, you have a sequence of random variables, variance sigma n square. You take the centered and scaled version. And then, there is this disk of Rn. So this Rn can vary with n, on which the characteristic function of xn doesn't vanish. And then you get a central limit theorem as soon as this Linux type quantity, this log characteristic function divided by Rn times sigma n goes to 0. So these are kind of off-the-shelf criteria which you can just try to check for each of your random variables xn in your sequence, for which you want to prove the CLT. And in fact, we have the quantitative control, the bound on the rate of the CLT, where the Kolmogorov spin of distance between the centered and scaled version of your xn and the standard Gaussian is bounded above by essentially by a constant times log characteristic function on your disk Rn divided by Rn times sigma n. You see, in this avatar of the result, you can see that in most cases of interest for which you can prove CLTs, except very few cases, mostly you have sigma n going to infinity. So as a result, so this log characteristic function usually we expect it to grow sublinearly. So you see, so there is a bit of an elbow room. So since sigma n is already going to infinity, depending on the circumstance, you are often allowed to take Rn to be shrinking to 0. So Rn doesn't really need to become large or even stay constant within in this setting. So that's a big advantage, because usually trying to demonstrate that the that the characteristic function is non-vanishing on a certain domain is often difficult, and if the smaller the disk on which you have to check this condition, the easier it is for you. So okay, so let us see some applications, and this brings us to spin systems. So just to lay out the framework. So suppose you have a d-dimensional cube. So think of Z, think of a hypercube in ZD, for example, or a box in ZD, and you have spins which are generally n-component spins, and the spins are distributed according to some compactly supported spin measure. So, for example, if it was a classical Ising model, then these spins would be plus or minus 1. Capital N would be equal to 1, and this mu0 would be plus or minus 1 with equal probability 1/2. Okay. But as we shall see, this covers a lot of other interesting examples, and including in particular continuous spin systems, or spin systems with continuous symmetries. And in fact, those are the models for which we believe that our result has the most interesting conclusions to tell us. So anyway, so let us get back to the spin system and discuss sort of how how the model is set up. So we consider general n-component spins, which are in principle continuous valued. And then we define the Hamiltonian, which are these coupling constants and these external magnetic field HXI. And so at this point, this is a completely heterogeneous model. So for instance, even the coupling constants can have different values in different components or different components. And the Hx is the external magnetic field, which can also be heterogeneous depending on the component of the spin that you consider. And then you consider the classical spin measure. So this is the classical Gibbs measure for spin systems. Beta is the inverse temperature, and it's e to the power of minus Hamiltonian times beta. Z is the partition function of the system, and as we shall see, this will have an important role to play. So what are the spin systems we have in mind? Ising model, of course, plus minus 1 valued spins with and the marginal law on the spins is plus minus 1 with equal probability 1/2. It also we also have in mind the XY model, which is the planar rotor model, which is spins taking values on the circle, and the marginal law of the spins is uniform distribution on the circle. And so mu naught is uniform distribution on the unit circle. Heisenberg model consists in spins taking values in the two-dimensional sphere, S2. And again, the marginal law mu naught, the marginal law of the spins is uniform distribution on S2. And then you sort of tilt this uniform measure by this Gibbsian function of the Hamiltonian. Okay, so fluctuation theory is well studied for the classical Ising model, but it is less understood for spin models with continuous symmetries, such as the Heisenberg model or the XY model. And the object of interest is the magnetization of the total spin, which is going to be denoted by S of lambda. So lambda, remember, is a box on which the spin system lives. And we show that S lambda satisfies a CLT upon centering and scaling as the box size goes to infinity with speed of convergence at the rate which is 1 over square root of the box size up to logarithmic factors. And the conditions for this result are ferromagnetic conditions. So we have a positive magnetic field, and then there are certain ferromagnetic conditions on the couplings. No, because we have magnetic field. And if you compare, I mean, the point is that the conditions are for the general spin system, so they are quite long and complicated to state. So let us summarize them by just saying ferromagnetic conditions. We also have, so this is for free boundary model, and we also have a version for a class of boundary conditions which themselves satisfy some ferromagnetic properties. But I would like to point out that the rate of convergence in CLT is comparable to the classical 1 over square root of the system size rate, which is the rate for IID random variables, and up to log factors. And because this is very far from an IID system, we believe that we are almost close to optimality. This log factor can probably not be removed. And we'd also like to mention that although this kind of a result, I'm not sure about the rate of convergence, but at least the existence of the CLT is known in the literature for the classical Ising model. But for the continuous spin models, such as Heisenberg model and XY model, it appears that this is the first CLT, even under ferromagnetic conditions. Yes. Yes. Yeah. I mean, all these results are usually proved by taking the cumulant expansion. The point is that you have to control the cumulants well, and it's a game of how well you can control the cumulants. Yeah. That log appears in the first place because of cumulant expansion. Okay, so okay, so we want to use our results to show these central limit theorems, so remember that in our situation we had to check two conditions. One condition one condition is on the rate of growth of the log characteristic function, but in our quantitative version it enters into the rate of convergence. Whereas even for the CL2 to even hold, we really need to check this crucial condition that in our disk of desired size, the characteristic function doesn't vanish. So in most models, this is kind of the hard part, or at least it is equally, at least as hard as the other growth rate condition. So let us dwell a little bit on how it works for the spin systems, and it will bring us to some interesting connections to Li-Yang theory. So you know, the total spin, it's an n-component spin, so it's an capital N-dimensional CLT. So we do it by the Wald's criterion. So we prove a CLT, one-dimensional CLT for every inner product of S lambda against every test vector. So let's just see how we go about it in the simple case when this test vector is the E1 vector. So it's the 1 in the first coordinate direction, 0 otherwise. So if you suppose we take the characteristic function of S lambda inner product with E1. So this is the form for which we want to prove the CLT. And then a simple computation shows that you can write this as the ratio of two partition functions. Okay, and basically we need to show that this doesn't vanish in a disk of certain radius Rn, and we want to make this Rn as large as possible. So in other words, we want to show that this ratio of partition functions doesn't vanish on a certain disk, and the denominator, of course, doesn't matter in this for this purpose. So really, it's the numerator. So really, we want the numerator not to vanish on a disk of certain radius in the variable u. So we really want to understand if you take the partition function of your spin model, and if you perturb it and make it a complex magnetic field, then how, what happens to the zeros of this partition function? And for this, this connects to the classical Li-Yang theory. Initially, classically it was used for phase transitions in spin models, but for us it will help us to check this condition of non-vanishing. So Li-Yang theorem, at least in one version, tells us that the partition function doesn't vanish whenever your magnetic field, which remember can be heterogeneous, falls in this particular quadrant of Cn for each lattice site. Okay, and if you look at this, then if you look at this condition, then if your magnetic field was already in omega n plus, then if you because this condition is an open condition, if you perturb, you are only perturbing the first component of the magnetic field H1 by u. Imagine u is a small number. So then, because it's an open condition, this condition will still, if this condition held for the original magnetic field under which you're considering the spin system, then after this perturbation or in the first coordinate direction, first component of the magnetic field, the condition should still continue to hold. So from here, you should be able to extract a small, perhaps a small disk in the variable u, in which the partition function doesn't vanish by the Lee-Yang theorem. And this is what allows us to establish the criterion that the characteristic function doesn't vanish in a disk of small enough radius. Okay. Okay, so let me skip over, for now at least, the ideas of the proof. And let me sort of move or show you another application of the quantitative Marcinkiewicz theorem, which is central limit theorems for alpha determinantal processes. So determinantal processes are, Bangalore is a place for determinantal processes. So probably most of you already know what they are. But for just for the sake of form, let me give you a quick reminder. And I will do it in the general setting of alpha determinantal processes. So think of alpha as a number between -1 and 1. And the first thing to do is to define the alpha determinant, which is this quantity. So if alpha was -1, this would be an actual determinant. If alpha was +1, this is actually a permanent. Okay. So this is the alpha determinant. And alpha determinantal process is essentially a point process for which the endpoint correlation functions are given by alpha determinants of some kernel and with respect to some background measure. So in most cases, you can take, after some normalization, you can take the background measure mu to be the Lebesgue measure on Euclidean space. So it's really the alpha determinant that's the important structure in this theory. And the definition of the alpha determinantal process is that the endpoint correlation functions are all alpha determinants. So for example, for alpha equal to -1, this covers the classical determinantal processes. Or alpha equal to +1, it is the permanental process, which is the bosonic point field, which is also of interest in physics and elsewhere. And for alpha equal to 0, this is actually reduces to the Poisson point process. So it covers, so this family of alpha determinantal process, although the name determinantal is in the title, but it covers determinantal that is repulsive, independent that is Poisson, and attractive, namely permanental process under one umbrella. And it also holds for other values apart from alpha equal to -1, 0, or 1. So it holds for other values in between alpha -1 and alpha 1. And for those, you can see a sort of a continuous, you can see a spectrum of point processes with degree of attractiveness or repulsiveness varying as you modulate alpha. And in general, the heuristic or the moral of the story is that if alpha is negative, you get a repulsion. The more negative alpha becomes, the more repulsive your point process is, and the more positive it becomes, the more attractive. So alpha -1 is determinantal, alpha equal to 0 is Poisson, and alpha +1 is permanental. And you have a range of processes in between. We want to study linear statistics of these processes. So linear statistic is you have a test function on your ambient space, and then you sum, if you have a realization of your point process, then you sum your test function, integrate it against the point measure. So this gives you a random variable which depends on the realization of your point process. And then in the usual way, as is popular in point process theory, you consider scaled versions of these linear statistics. So these are called linear statistics, these test functions integrated against your random points. And we consider scaled versions of these test functions. And as the scaling goes to infinity, we want to understand what is the fluctuation behavior. And so for example, there has been a lot of results. It is of great interest in the theory of determinantal processes and random matrix theory, where the asymptotics of these linear statistics can be put to good use. So without further ado, let me state the theorem. So suppose you have a nice test function, and then your linear statistic satisfies a CLT upon centering and scaling with where the rate of convergence is logarithmic in L times L to some power, and this power depends on the model. So I will give some examples in the next slide. But this is roughly the moral of the story, and I will mention in a couple of slides as to how it connects to the quantitative Marcinkiewicz theorem. Before moving on to the specific instances, let me remark that our result is particularly relevant when the ambient dimension is bigger than or equal to 3, where structural alternatives such as connections to random matrix theory are not available. Because in dimensions 1 and 2, and particularly if it is determinantal, you can leverage connections with random matrix theory. And once you have specific structure, you usually expect to have much sharper results. Whereas this is a sort of a general hammer, and it works particularly well when you do not have these specific structures to play with. Okay. And it covers a broad class of kernels, in particular kernels with slow spatial decay, such as Bessel kernel, and in general dimensions. And we obtain explicit rates of convergence in a wide spectrum of models. And even for determinantal models in low dimensions, CLTs are known, but rates of convergence are less studies. There are less results on those. So here we obtain explicit rates of convergence thanks to the rates which are suggested by the quantitative Marcinkiewicz theorem. So for example, so let's take an example. So here, suppose D is bigger than 2. So that's the domain, that's the regime which is of greatest interest to us. And your kernel has some decay condition, which is basically integrability of the order 3/2. And then, so this is some kind of sort of extensiveness condition in each direction. So there should not be any direction in which your kernel kind of completely collapses. Then under the above conditions, the linear statistic satisfies a CLT with a rate where this power is 1/2 D minus 2. So here is another example of another consequence of our result. Suppose you have the Bessel kernel point process. So this is determinantal, and D is bigger than 1. Actually, the most the interesting case is when D is bigger than or equal to 2. So we have that the linear statistic satisfies a CLT where the rate of convergence is of the order log L times L to the minus D minus 1. Okay. And the Bessel kernel is a sort of a kernel of slow decay. It has zeros and it is oscillating. So it has many problems. So for example, there has been a lot of work in the continuum percolation literature where people are interested in percolation properties of Gaussian random field with the Bessel kernel, and this kind of slow decay and oscillating nature of the kernel poses a great problem. And similarly, in the case of CLTs, also it creates complications. So our technique allows you to obtain CLTs at a reasonably fast rate for such kernels, and in particularly when the dimension is general, for which alternative methods are limited. Yes. Exact variance. Okay. In terms of phi. No, this is a bound. So in terms of phi, we did not estimate. In some sense, it's a general. So in no case do we try to compute the exact variance. I am not sure even if it is computed. I don't know if it is known, but I would imagine that up to log factors, it's probably going to be this. Let me try to sort of point out what is the connection with what we have been discussing so far. So once again, if you try to use the quantitative Marcinkiewicz, so maybe we can review the Marcinkiewicz theorem a little bit. So once again, if you want to use the quantitative Marcinkiewicz theorem to obtain CLTs for this kind of point processes, you need to check that the characteristic function of your linear statistic doesn't vanish on some disk of suitable size. So for this, we need to have a handle on the characteristic function. In the case of the spin models, remember that we had a handle on the characteristic function first by identifying the characteristic function with the partition functions for a complex magnetic field, and then we took help to invoke the Liang theory in order to understand the zeros of partition functions with complex magnetic field. Here, what we do instead is that we invoke we use the there's a determinantal formula for the moment generating function, and under some suitable decay assumptions on the characteristic function of these linear statistics. And this determinantal formula is essentially due to Shirai and Takahashi, and you see the structure here. So basically, once you have this determinantal formula, you can try to use this formula to sort of verify the no zeros condition. And of course, the better you are able to do, the larger you are able to take your domain of non-vanishing R. And actually, in this case, the domain of non-vanishing can be taken to be essentially of the order of inverse of the L infinity norm of phi, which is of the order 1, basically, because as L increases, the L infinity norm of phi remains constant. And essentially, we are reduced to verifying, in order to use the Marcinkiewicz theorem, quantitative Marcinkiewicz theorem, we need to verify that this goes to 0. And in fact, the order of vanishing of this quantity will give us the rate on the Marcinkiewicz theorem. So generally speaking, it is under mild assumptions, it is not so hard to check that the log-log characteristic function grows at most logarithmically. And the harder component to verify or demonstrate is that when is the order of this standard deviation sigma L of the linear statistic, and it grows, and we show that it grows like some power L to the eta, which depends only on the model. And we have given some examples on what the value of eta can be in these particular cases as instances. So yeah, so this is what I had to say for today, and I'm almost at the end of my time. So I have some more, more discussion on the ideas of the proof for the spin system application, but I think it is quite substantive, so maybe it's not a good time to get into that. I'll just end my talk here, and thank you all for listening.
Are there any questions?
Yes, yes. I don't remember. I don't know off the top of my head, but Gaussian case is the most interesting one. Yeah, that, I mean, in the sense that that's the one for which there has been the most extensive literature. I do not recall seeing any other. I do not recall any other identification theorems like this. But it is correct that if there is any identification theorem, then of course it's natural to ask for a quantitative version of that. But in this case, but I am not sure if the kind of the proof techniques would carry over, because yeah. So if you look at it in terms of the growth of the log-log characteristic function, as long as log-log characteristic function is sublinear, it's Gaussian. You are in the Gaussian domain, as we saw. And if it becomes linear or higher, you go somewhere else. But those random variables are structured very differently. So for example, when it is actually linear, it's Poisson, which is discrete. So maybe the techniques need to be different.
Are there other questions? So I had a naive question. Can you use this framework to derive concentration inequality, like sub-Gaussian?
That's what we are working on. So please don't steal our project.
Okay. If no more questions, let's thank Subhro again.
Thank you.
And we will resume at 11:10.